So when we left off yesterday, we were talking about this idea of a confidence interval, and the whole point is because you go out and you take a sample. The issue is that that of course you understand that that's just a sample of the population, and so your estimate is probably not the truth, right? There's some error. You've probably slightly underestimated or probably slightly overestimated the truth. And so what we do is we say, okay, well, this is my best guess, but the truth could be maybe a little bit less or a little bit more. So we came up with a way to sort of establish boundaries, like a lower bound and an upper bound, and say this is where I think the truth probably is, somewhere in this range. And the way we do that statistically is we use this concept of confidence, and we rely on the central limit theorem to give us a good boundary, because you don't want to make your interval too wide, because then it's not informative, but you don't want to make it too narrow, because then there's a good chance you're going to miss the truth. So what we do instead is we use that normal distribution, and this is the general formula we came up with yesterday after a little bit of discussion and some justification. All right, for proportions. So if you're trying to estimate a population proportion, like the percent of people who work full time, right? Then you would have some population proportion estimate. You'd have some multiplier, and then this is that sample standard deviation. And this multiplier comes off the z-table, but we looked at, and your z-table actually gives it, but we looked them up. We looked at some common confidence levels and the multipliers that are associated with that. So, and then we introduced this concept of sort of like an alpha level. Think of it sort of as your error rate. It's the complement of your confidence. So, all right. So I think we did an example of that. Right, we were talking about Valentine's Day or something else here. And then what we noticed is that what happened when we wanted to make, what happened if we wanted to have more confidence? What did we have to do?
Widen it.
We had to widen it, yeah. So like in this example, they had polled 1,000 people, yeah. But what would happen if we sampled more people though? What do you think is gonna happen to this interval if we sample more people? What do you hope happens? We kind of talked about it yesterday. If you take bigger samples, what do you think you can do to your interval?
Bring in smaller.
Yeah, you would hope, like you take more samples. So you would hope as you take more samples, you should be more confident, right? Or you should feel more comfortable with your estimate. So you'd hope that that interval would shrink as your samples go up. That's what you hope would happen. And I think it's what's going to happen, but let's just see. So let's say we did this exact same. Let's say instead, what would have happened if rather than 1,000, maybe n was 2,000, or maybe n was 4,000, but our sample proportion was still 18%. Yeah? So instead we took a bigger sample and still found 18% who just like dreaded Valentine's Day. Yeah? Okay? So what would happen to our interval? Let's see if it does get narrower. I think it will. So the formula, remember, is p hat plus or minus z alpha over 2. And let's just fix our confidence level. Let's just go with that 95% confidence. Okay. So I'll write down the formula here, and then we'll just drop in our values. Okay. So if we would have taken 2,000 samples, our sample proportion, say, was still 18%. For 95% confidence, this is going to be 1.96. Our sample proportion was 18%, which means 1 minus that would be 82%. And our sample size here, we're considering what would happen if it would have actually been 2,000 people. Yeah? And so what's going to happen here? This with this 2,000 downstairs, what do you get for this whole like plus minus term? So go ahead and take a second or a couple of seconds and calculate that, and tell me what you get for that whole thing. Do the stuff under the square root it, and multiply by 1.96. Any takers?
I got 0.0168.
So 0.0168 is 0.017, say, if we rounded it 3 decimals? Okay, so 0.01. Dude, this is a mysterious computer. Okay, there it is. I was like, okay, that's weird. 0.017. So that would mean if you do 0.18 minus that, what does that take you down to? 0.163 and up to 0.197. Did I do my mental math correct on that? Somebody want to confirm that for me? Some days mental math is easy, and some days it's not. Yeah? I think I did that right. Okay, thank you. So now notice how does that compare to our 95% confidence interval when we did 1,000? Our percentage went down to what, 15.6 and up to 20.4, and now it goes. It only goes down to 16.3 and up to 19.7. So what happened to our confidence interval? Did it get narrower or wider? Did it narrow or widen? Got narrower, right? In fact, and so what should we expect to happen if we would have bumped the sample size up to 4,000? Hopefully it's going to get more narrow even, and we can see that. So plug it into the formula. Assume we still got 18%. We're still doing 95% confidence. The only thing that's going to change is our sample size downstairs, right? So now it's going to be 4,000 instead of 2,000. All right. So take a couple seconds and see what you get from that. Do 0.18 times 0.82 divided by 4,000, square root that, and multiply by 1.96. 0.012. 0.12. So what happened to this value that we add and subtract? It got smaller, right? Which means that our interval is going to narrow in a little more. So now it's going to be 0.168 up to 0.192, right? So our interval is like shrinking in. Back when it was, if you think back before, when it was 1,000, right, our interval was 0.156 up to, I can't remember, 204. Yeah. So each time you take more samples, at 1,000 samples, it was like from 15 to 20%. Then it came into like 16 to just under 20%. When you got even bigger, it made its way into like 17 to 19% almost, right? So it's shrinking every time you take more samples, which is what you want, right? Okay. So this is the general relationship. There's two ways that you can affect, and we've seen them both. So there's two ways that you can affect the width of your confidence intervals. So what are the two ways you can affect it that we saw? One is the one we just did, and what was that?
Sample size.
Yeah. So if you increase the sample size, what happens?
Narrows the.
You get a narrow interval.
Yeah.
Mm-hmm. Which makes sense, right? The more people you sample, you hope the closer you're getting to the truth. What's the other way? I'll make this a star so it's not also an arrow. What's the other way that you can change the width of your confidence interval that we saw? We saw it yesterday.
Change and multiply.
And what does that mean? We call that changing the what?
Like how many standard deviations you got or whatever.
Uh-huh. And that's associated with the confidence level. Yeah, we changed. Yeah, So if you say if you want to increase your confidence, then what do you have to do to your narrow? So if you want to go from a 95% to 99%, what do you have to do? You have to make it wider. Yeah. Right. So there's two things that control your width. Your sample size. So the more samples you take, that narrows your interval. But at the same time, if you're trying to become more confident, you're also going to have to make it wider. So there's a trade-off between confidence and sample size. And they work against each other, I guess, sort of in a way. All right. Now, of course, you could do them both. You could increase your confidence and still keep a nice narrow interval. It's just that what would you have to do at the same time?
You have a massive sample size.
Yeah, you'd have to increase your sample size in conjunction. So you can increase that confidence and increase the sample size. So that would be one way to offset the fact that your confidence would make it wider. All right? Does that make sense? Yeah. And so now so typically this idea, your confidence is usually picked in advance. So that's usually not actually really an option. Because typically you kind of decide ahead of time how much confidence you want. When we get to chapter 10, I mean, what if you say that you're going to pick your confidence ahead of time, then what confidence level do you think you would always pick?
95.
Maybe 95. Why?
Because anything outside of 5% is unusual, and then
Why not 99% confident though?
then you're out. You have to make it wide enough to where the data is not as useful.
Okay. Well, then what if I want a narrow interval? Why don't I just say 90% confidence then?
Because then you're giving up too much margin.
Yeah. So there's a trade-off, and actually, it turns out 95% is not a bad way to go, but it depends on the application. And what we're going to talk about in chapter 10 is we're going to talk about, why would you pick lower confidence or higher confidence? Sometimes you would want higher confidence, and sometimes you'd actually rather have lower confidence. And so we're going to talk about that when we get to the next section. So for now, just know that confidence is pretty much always picked in advance. And we'll talk more later about why or how you would pick your confidence level. Now, you could imagine then, so if you look at the formula, so you look at this formula for the confidence interval, right? And your goal would be what? What kind of intervals do you really like? Wider intervals or narrower intervals? What's more useful, really? Would you rather have a lot of error or not so much error? Yeah, you usually have a goal probably like, I don't really want to have, a ton of error because that would make my estimate useless. And which of these things do you actually have control? So let's say if you pick your confidence in advance, what do you actually have control over in this whole formula? You only have control over one thing, and what is it?
The sample size, really.
Yeah, so this is really the only thing you really have control over. Because based on the application, you're gonna pick your confidence in advance. So that's going to fix, this z-value is fixed. Can't change that once you pick your confidence. You're going to go take a sample, and it's just going to give you a proportion, p hat. You don't have any control over that. That's just what your sample tells you. So the only thing you really control is your sample size. And so one thing you might ask, what's a question, before you go out and you do your analysis, what might you, besides your confidence, what do you need to decide on? If this is the one thing you control, what do you have to make a decision about? Yeah, you got to decide how many people you want to talk to, right? Because you don't want to talk to so few people that your confidence interval is useless, but you don't want to talk to so many people that you're wasting your time. Because you can see here, look at this example. We went from 2,000 to 4,000 people. And how much did it really affect our interval? Like what, maybe 0.5%? By doubling our sample size, all we really gained was 0.5%. Is that really worth it, necessarily, depending on what your question you're trying to answer? Right? So it's not necessarily worth your trouble to always go with huge sample sizes. So you have to decide how big to make your sample size. So we have a term for this big chunk that we add and subtract, and you've heard it before. Okay, that's what we call the margin of error. So this chunk right here, that value that you add and subtract, that's the term when you read a newspaper. That's what they're calling the margin of error. Like that. So you read a poll and it says, you know, so-and-so is leading by 4 points with a margin of error of 2.5%. That's this chunk. It's saying that if you constructed a confidence interval around that value, so say so-and-so is expected to get 54% of the vote with 2.5% margin of error, then you would take 54%, and if you want to construct a confidence interval, it would be down 2.5%, up 2.5%. That's what they're referring to when they say margin of error. Okay? Now, of course, if you're thinking about going out and sampling, if this is your margin of error, then one thing you might want to do is you may want to sort of like bound your error by taking enough samples. Right? That may be a goal that you have. So let's say that's your goal. You say, you know, you're going to go out, you're going to invest this time in taking a sample and doing a statistical analysis. It might be expedient for you to say, okay, if I'm going to take the time to do this, I'm going to do it right, and I want to make sure I take enough samples to get my margin of error down to a point that makes sense, you know? Because that's really, what if you spend a bunch of time taking a sample and you come back and your margin of error is like 6% because you didn't sample enough people, and now you're like, well, dang, that was a waste of time. I wanted something more accurate, right? So our goal sometimes is to bound this. Well, luckily we can kind of do that. So let's think about this algebraically here. So again, this right here, that's fixed, right? The z alpha over 2 once you set your confidence. The problem is that before you go out and you take your sample, do you actually know what your sample proportion is going to be? You don't, right? I guess that's a problem. Okay, so here's the nice thing about it though. So where can your p hat? What's the maximum and minimum value of a sample proportion? Yeah, it can only go between 0 and 1, right? So it can't go anywhere between 0 and 1. It turns out, if you look at this quantity, p hat times 1 minus p hat, so like whatever p hat is times 1 minus p hat, it actually, there's a maximum value it could possibly be, and it reaches its maximum value right here at 0.25 when p hat is 0.5. So this is the max it can be. You would actually need like a little calculus or something to prove that, but we're not going to do that. But you could take, hopefully you'll just take my word for it. You can try it in your calculator. You know, try like 0.2 times 0.8 and 0.4 times 0.6 and 0.45 times 0.55 or something, right? And see what happens. Eventually you're going to realize that the most you can possibly get is when you do 0.5 times 0.5. That's as big as you can get. Okay, so what we do is we say, okay, we want to be conservative, right? We want to definitely make sure we take enough samples. And so what we do is we say, okay, so we're going to go ahead and we're going to use a conservative estimate, and we're just going to use 0.5 times 0.5 because we know that's when it's maxed out, and then we can actually solve for n here. So you have what do you have? You would divide by z alpha over 2. If I'm trying to solve for n, what would I do next? I could square both sides, right? So then you'd end up with your error over z alpha over 2 squared equals, well, 0.5 times 0.5 is just 0.25 over n. And then how would you how would you go from here? How do you solve for n here? I need to get it out of the denominator basically, right? So I need to multiply over here. And then I need to, you can cross multiply here. What you're going to end up with is basically n 0.25. When that comes to the other side, it's going to flip. And then this is the formula we use. So we solve it for n, and it's a conservative estimate, so which means that basically if you take that many samples, there's a good chance your error will actually be below what you wanted, but at least it's not going to be more. All right. So this is how ahead of time we decide how many we're going to sample. So you pick your confidence level, you pick your margin of error that you want to get down to, and that informs how many people you need to talk to. All right. So let's do an example here. All right. So let's say you want to, you plan to estimate with, let's say 95% confidence. You want to know the proportion of, say, CBC students who work full-time. Okay, so this is your goal. I want to figure out what percent of students work full-time. I don't want to have to sample any more students than I have to. So let's say your goal is to, let's say, have a margin of error no more than 3%. That's your goal. So I want my margin of error to be no more than 3%. The question is, how large should n be? So you picked your confidence ahead of time. You know the margin of error you want to get down to. You say, I'm going to go do this estimate. I'd like to be within 3%. I'd like to have that 3% margin of error. How many samples do I need to take? The way we're going to do that is we're going to use this formula. Okay. So in this case, what's going to be our z alpha over 2? Yeah, so that's based on our confidence. So it's going to be 1.96, right? That's the multiplier for 95% confidence. What's the error rate that we want? So as a percent. And so we always deal with our proportions or our percentages in proportion form, decimal form. So it's going to be 0.03. That's going to end up meaning squared. And then we're going to multiply that by 0.25. So take 1.96 divided by 0.03, square that, multiply by 0.25, and what do you get? I can check it too, but I'm guessing you guys probably would get 1067. And what should you? So this is decimal. You can't sample decimal peoples. So what do you think you should do for sample size? Which way do you think you should round for sample size? Yeah, so for sample size, regardless, we always round up because we want to be conservative. We want to make sure we definitely get enough people. So then you would probably say how many people? Yeah. It's a lot of people. Yeah. But to get that 3% margin of error, that's a reasonable upper bound on where you need to be. All right? Okay. So let's say you actually did this experiment, right? So you said based on this, you go out and you actually decide to take the sample, and you manage to get 1,068 people. So I'll just say continued. Let's say that you go out and you actually got those people. So you sample 1,068 people, and of your sample, say 18.8% work full time. Now go ahead and calculate that 95% confidence interval for the true proportion of students who work full time. So you go out, you actually get those 1,068, 18.8% of them work full time. So now, how are we going to calculate the confidence interval? What are we going to use? Yeah, we got a formula for it, right? So remember, it's just b hat plus or minus. In this case, it's 95% confidence. So that's just going to be 0.188 plus or minus 1.96 times the square root. So this is going to be 0.188. 1 minus that is going to be what's going to be 812 all over 1068. So take a couple seconds. Actually, evaluate that margin of error for me, and let's see if our margin of error really was as low as we wanted it to be. Remember, we wanted it to be under 3%. That was our goal. Let's see what our actual margin of error came out to be. There you go. 0.023. 0.023. So this was our actual error rate. You know, is that below where we wanted to be? Is that reasonable to us? Yeah, we said we wanted to be 3% or less. So we went really conservative. That's why we used that 0.25 multiplier. So we went and took that amount of samples. It turns out we ended up with a nice a margin of error much less than what we needed it to be, and that's okay. I mean, smaller error is always better than larger error. All right. So then we go ahead, and if you go ahead and put that together, that would, if you subtract that, that would take you down to what, 0.165, and up to 0.2. Is that 11? Yeah. Yeah. Okay. So then you can interpret this. Right? You would say something like, we always start out by stating our confidence level. So we're 95% confident, and then we say what we're actually estimating, the true proportion of CBC students who work full time. And then we report our boundaries. So we say, okay, so that's between, what is that, 16.5% and 21.1%. Okay. And it doesn't really matter if you report it as a proportion or a percentage. I typically report it as percentages just because that's what most people are more familiar with. In a non-mathematical sense. You guys are all pretty comfortable with proportions because you've been taking math classes for a while now, but a lot of people haven't taken math classes recently as you, so they're more comfortable reading percentages. All right? Okay. What questions do you have about that? So once you know the procedure, it's actually not terribly difficult. It's just a matter of using the formulas. Up front, you pick your confidence and your margin of error. That drives your sample size selection. Once you have your sample size, you go out and you get it. You calculate your statistic. You just use your other formula. And now, with basically no information, right? We started out with nothing. Now we've collected a sample, we've made an estimate, and we've come up with a nice, reasonable interval that gives us a nice range where we expect the truth to be. And we have some really sound statistical, mathematical, probabilistic ways to justify that, right? We didn't just pull it out of thin air. Okay, we have a nice justifiable way to do it. So, yeah, it's pretty cool. Yeah.
So I have a question on the last,
Sure.
like the right hand side of how you got those numbers.
Which one? The bounds or this one?
For both sets.
So this right here,
Yeah.
this came from all of this madness.
So 1.96.
Yeah, and on your calculator, it's best to work it backwards. So you go like 0.188 times 0.812, divide that by 1068, then take the square root, then multiply by 1.96. That should get you 0.023.
Okay.
Yeah.
And then where is
Yeah, and then exactly, subtracting it gets you down to there, adding it gets you up to there from 0.188. Yeah, okay. Now, does this necessarily mean that the truth is definitely between those two values?
No.
Does it?
What did you say? Repeat the question.
The question was, is it if this were real, like say I actually did this, can I verifiably say that for sure the proportion of CBC people who work full time is between 16.5% and 21.1%? Can I say that?
No, because now 95%. I have a 0.95%.
Yeah. Yeah, exactly. I'm not 100% confident. I'm only 95% confident. So the truth actually might not be anywhere in there. I mean, the truth actually could be lower or higher than that. But at some point, right, when you're trying to estimate something that you can't possibly know for sure, you have to be happy with some level of uncertainty. And so if I'm trying to make decisions, say as a college, like I'm a college administrator, this is, at least I have something to work with, right? So is the truth necessarily in there? Not necessarily, I don't know. But is this at least a reasonable range that I can use to make predictions or calculations about my college? I think so, right? You could justify that. And in fact, really, a lot of people misunderstand what a confidence interval is saying. All that a confidence interval is saying is this. What does 95% confidence really mean? So what it really means is that, the true proportion exists, right? It's out there, right? If we could stop time right now and we could ask every single CBC student if they work full time, they would give us an answer, and I would know in this instant what the exact proportion of full-time workers is. Yeah? It exists. But what happens is that, okay, we can't do that. So what do? You sample one time, you get a p hat, and you construct an interval, right? You sample a second time, you get another p hat, maybe here. You construct an interval, and that's what you get, right? You do another sample, and maybe this time p hat is about here or something, and you construct an interval, right? And so sometimes your intervals are going to be a little higher, sometimes your intervals are going to be a little lower, and then every once in a while, what's going to happen? What's going to happen every once in a while? So far, this was a little underestimated, but I caught the truth at the top. This was a little overestimated, but I caught the truth in the bottom of my interval. So eventually, what's going to happen, though? I'm going to miss it. Well, sometimes I'll get really close, but eventually what's going to happen is I'm going to end up with a p hat just based on random sampling that's really big or really small, and my interval is just going to completely miss the truth, right? It's just going to happen sometimes. Now, the question is, how often is this going to happen where it catches? Yeah, this is going to happen 95% of the time. And how often is this going to happen?
5%.
Yeah. That's what 95% confidence means. It means like if you were to do this procedure over and over again, 95% of the time you'd catch the truth, 5% of the time you'd miss it. But when you only take one sample, can you really be sure whether you're in this scenario versus that scenario? No, you can't know. So you just have to be happy with the uncertainty. You just have to accept the uncertainty. That's the best you can do. Unless you want to up your confidence or up your sample size, right? If you want to up your confidence and up your sample size, you could do a little bit better, but then that gets exhausting. Eventually, we're already sampling 1,000 CBC students. How much better do you want to get? Do you really want to sample 4,000? I mean, eventually you're getting to the point where you're basically sampling everybody. And that's just too time consuming. So, all right. Any questions about confidence intervals? Do you feel like you can calculate a sample size and then calculate a confidence interval? Okay. So there's plenty of practice problems on the homework for that. Now, all right, so now the thing about it, though, is that if you remember, the proportion is not the only thing that we wanted to estimate, right? So we talked about calculating proportions, but we also talked about calculating another statistic, and what was that other statistic we were interested in? Not a percent or proportion, but a what? Maybe I'm interested in the sample size is important. But typically we're trying to estimate a number. So I could be estimating a percent, but I could also be estimating what? We talked about it in chapter 7, 8. The central limit theorem applied to two things. It applied to sample proportions, and it applied to sample what? Mm-hmm. Yeah. We talked about proportions, but we also talked about averages, right? Sometimes we're interested in estimating averages. So what if our goal is not to estimate a proportion P? What if my goal is to estimate a population mean mu? Right? So we've talked about two main types of statistics here, proportions versus means. All right? So how do we do that? Well, again, we're going to have to go sample, right? And then from that sample, we would calculate what? What number would we calculate from our sample if we're interested in population mean? So we got a whole bunch of numbers. I want to estimate the mean, so I'd probably calculate the sample mean. Call it X bar, right? Now, the nice thing about this is, well, not the nice thing. This is really analogous to what we already talked about with proportions, though, because if I go get a sample and I calculate a sample mean, is that sample mean actually equal to the population mean? Probably. Do you think it's going to be exactly right? Probably not, right? It's probably either a little underestimated or overestimated from the truth. So again, this is probably close, but wrong, right? It's probably somewhere close to the truth, but it's probably not actually the truth. Okay? So again, we probably could do what with that, though? Rather than just giving me one value, maybe we could do what? Just like with proportions. What do you think? Rather than give me one value and then say, hey, Ryan, this is my best guess and it's wrong, what could you give me?
A range.
Yeah, give me a range, like an interval, right? So the nice thing about this, though, is so we already laid the groundwork for this process, though. We'll just calculate an interval around our sample mean. And we already know how to do that, actually, because the whole idea behind our confidence interval came way back. So I'm about to scroll through like a bajillion slides here. Here, right? From the central limit theorem. We said, hey, the population proportion is centered around the true proportion with this standard deviation. I know 95% of the time it's going to be within 1.96 standard deviations. Let's make that our interval. Well, the nice thing here is that for sample mean, the central limit theorem also applies. So the central limit theorem, it says x bar is approximately normal with centered around the true mean standard deviation given by sigma over root n, right? You needed that result to calculate some probabilities in Chapter 8 on the quiz you guys did over the weekend, which I hope we have graded by Thursday. That's my goal. Probably not tomorrow. Thursday is my goal. Okay? So anyways, the nice thing, though, is that, so that's telling us x bar comes from this normal distribution, right, centered around mu with a standard deviation of, sigma over root n. So then we can just use our confidence interval formula and say, okay, let's use the same strategy, but instead of this being p hat times 1 minus p hat over n blah, 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 we got that because it was sample standard deviation. We'll just use our sample standard deviation. And boom. Easy peasy. There you go. Confidence interval for sample means. Same justification we used for the proportion, but the justification isn't really that important. None of you guys are probably going to remember it anyways, so I don't care. So I'm just going to give you the formula, right? But just trust me, okay? If you trust me. If you don't trust me, you can come to my office. I'll convince you. All right? All right. So it worked. Okay, it works. Now, yeah. So there's a problem with this formula, though. Yeah. And
You just told us to trust you.
well, it works. No. This formula 100% absolutely works, and it gives you the confidence you think it's going to give you, and everything is wonderful. But there's actually a practical problem. It's the same problem we had in our other confidence interval formula, and there's a problem here.
Really only control the one thing.
Well, we can only control one thing, really. Yeah, as a sample size. The z value is fixed. Now, remember, what's your goal here? What's our goal? Our goal is to estimate a population mean, mu, right? Now, looking at this formula, though, what value does this formula assume that we know?
The standard deviation.
Yeah, right here. What is sigma? Sigma is, this assumes sigma, right, which is the population standard deviation, is known.
But if you knew that, wouldn't you almost know the mean of the population too?
Exactly. How on earth would you somehow have enough data to know the population standard deviation and yet somehow be completely ignorant of the average? How would you, that just doesn't even make sense, right? It's just not even reasonable. So this formula is great, except for it includes a value that we pretty much don't know, almost guaranteed. There's limited circumstances where you could kind of justify this. So I'll give you an example. Like, suppose I don't know something about CBC students, but I believe that CBC students behave like maybe our population is similar to other colleges in the state. And maybe there's a lot of data on other colleges in the state. So I assume our standard deviations look like their standard deviations. Maybe. That might be reasonable. But typically we don't know it, okay? So this is a really big problem. Okay? Yeah. So we need to solve this problem. Do you guys know what Peg plus Cat is? And you guys have kids? Nobody in here has kids that watch Peg plus Cat? Okay, never mind. My kids watch PBS. It's Peg plus Cat. It's a good show. Teaches your kids about math, right?
Why you think it's a good show?
It's a great show. It teaches them, yeah, anyways, it's a great show. So my kids watch it, but that's what they say. They say, this is a huge problem. It is a huge problem. Okay? All right. So anyways, but we can solve it. Actually, we're not going to solve it. We're going to let some old dead guys solve it. Because they already did it for us. Okay? So this was a problem they had. Now, we're not completely out of luck. Not completely out of luck. Because we could estimate this value, couldn't we? Couldn't we estimate the population standard deviation? Could we?
I mean, maybe.
Maybe. What would be a good estimate? So I go out, I take a sample, I got like 500 observations, I can calculate an average. Could I estimate a standard deviation from that data set?
You can figure out what the standard deviation in that data set is.
Yeah. So we have a sample, and we know how variable it is. We could just calculate the standard deviation of our sample. So this is the proposal. That's a pretty natural proposal. You say, okay, so sigma's unknown. So how about this? Let's just estimate sigma with what we call S, right? You know, that whole, this stuff, remember? Sample standard deviation, right? I got a whole bunch of data. I got a computer that can calculate it in like half a millisecond. So plug your data in, get a sample standard deviation, boom. And it turns out this is actually a good estimate. It really is. Turns out that S is what we call unbiased for sigma. In other words, it's a good guess. It's a good guess. Yeah, it turns out it's a pretty good guess. So you got some data. You calculate the sample mean. You calculate the sample standard deviation. You say, hey, this sample standard deviation, it's a pretty good guess for the true standard deviation. And I know that if I knew it, what could we do instead? So instead of putting the population standard deviation in that formula, what do we do instead maybe? We just say, you know, I don't actually know that. But hey, I got a pretty good guess. So maybe I just do this. Right? So we'll just use S instead of sigma. Seem like a good idea?
Sure.
Seems like a pretty good idea to me.
I trust you.
Thanks. That means a lot to me.
Well, you control my grade.
I control your grade. So, you should always be skeptical, though, right, of the people who have power over you, maybe, or something. I don't know.
Well, there's always skeptical, but you gotta
You're skeptical. Yeah, you're skeptical of me, but you're just not going to say it because I control your grade now.
Right.
Yeah,
You gotta let them know that you trust them, but you don't.
okay. Right. So, well, I appreciate your trust, whether it's genuine or not. But it turns out it doesn't matter because actually this doesn't actually work really that well. There's a problem. Okay. Yeah, there actually is a problem with this. It doesn't really work as well as you think. And here's the problem. Okay. If you do this, this doesn't actually have the confidence you think it has. Right? So it's not quite there. So like you might think you're calculating a 95% confidence interval, but in reality, you might only be calculating like a 90% confidence interval or something like that. And the problem is that this standard deviation is estimated. So sometimes it's going to be too big or too small and you don't know. Right? That's a problem. So somebody already solved this problem for us, luckily. Okay. So they had this actually, and this is actually a really interesting story. And maybe you've heard this story before. I don't know if I told you this story. Did I tell you about the guy who worked for Guinness Brewery? Did I tell you that story? Okay, so this was like back in the early 1900s, and the guy's name is Gaussian, and he said they needed to solve. They had this problem. What they were trying to do is they were trying to use statistics to basically make like more consistent and better beer. That's what Guinness wanted to do. They said, you know, We want to make the best beer. We want to make it consistent. We want to make sure when anybody drinks Guinness beer, they're getting Guinness beer and whatever, right? That was their goal. So they hired a statistician from, I think it was Oxford. I can't remember. I can't remember what English university he's from. Anyways, they hired him to come to Guinness and do work for them and said, look, we need you to figure out a way to do this. All right. And so Gaussian comes. He's very well aware of the central limit theorem, but he also understands this problem. The problem is that this doesn't have the confidence that they think it's going to have, so it's not really good enough for quality control. So what Gaussian did is he looked at this. He said, okay, I know that when you take, I know you don't have to necessarily write this down. All right. I know that when I look at this, I take a sample mean minus a population mean divided by the sample standard deviation, that this basically is a z-score, and I can do things on the z-table with this. Right? That's what he was looking at. So that's really cool. But the problem is, he says, but what happens when, I start doing things like this? That was what he was trying to look at. What if I estimate it? And what he found is that the distribution of these things didn't quite look like a z distribution. What it looked like is, the z-scores, your z-score has a nice bell shape, right? And what he was noticing was that when he was looking at, that's not what I want. When he was looking at his, he was noticing that his looked kind of normal, but it had what we call heavy tails. It looked more like that. So it had these heavy tails in the sense that these weird outlying observations popped up more often. And the reason they pop up more often is because back here I'm only estimating one thing, a mean, whereas here I'm estimating two things. So there's a chance that your mean and your standard deviation could be really bad guesses for the truth. And so there's more uncertainty, and so it had these heavy tails. So what he did is he said, okay, well that's okay though. Let's just give this a name. And so what he called this is a t-statistic. And he came up with what he called the t-distribution. And we have now something called a t-table. All right. Yeah. So rather than using a z-distribution, a z-table, he came up with this other distribution called a t-distribution that looked like a z-distribution but with heavy tails, so that he could keep the confidence that he needed in his confidence intervals, basically, or in his decisions. All right. And anyway, so normally, so if you look in your book, actually, this is sometimes called, they call it students' t-distribution. Okay. And normally, if you come up with something really cool in math, people will name it after you, right? So if I came up with some really cool whatever distribution, they would call it like Orr's distribution or whatever, or something like that, which I'm not going to do that because I'm not that smart, but some people are, and they come up with cool stuff. Like the normal distribution is sometimes called a Gaussian distribution because the function was found and fit by Gauss, who was a mathematician. So you would think this would be called Gauss's t-distribution, but it ended up being called students because what happened was, so he came up with this really awesome t-distribution. And so Gaussian says, hey, I got to publish this. Other statisticians need to know about this, so they can start using this in their own statistical analysis. And Guinness, they said, well, that's cool. You can publish it, but you just can't put your name on it. You can't put your name on it. That's what they said. Because why? Why do you think they didn't want to put a name on it? Why wouldn't Guinness want Gaussian putting his name on the distribution? What do you think? Because they're jerks? Yeah. No, it's not that. What do you think?
They probably didn't want other beer companies to copy the formula to get better beer.
Yeah, that's the thing. Because if he puts his name on it, right, it's this big groundbreaking discovery in statistics, and everybody says, whoa, Gaussian came up with this. Wait, where's Gaussian at right now? And they say, oh, he's been working at Guinness for like 3 years. And then all the other breweries are going to be like, wait. So Guinness is using statistics to make better beer? Maybe we need to start using statistics to make better beer. And Guinness didn't want them using statistics, right? They didn't want other breweries to know that they were using this t-distribution to make their beer better and more consistent. and so they wouldn't let him put his name on it. So when he published it, he just published it anonymously, and he signed as the author. He just signed himself as student, and so now it's known as student's t-distribution. It should actually be Gaussian's t-distribution, but anyways, Guinness didn't want then anybody to know they were making really good beer this way. Turned out it worked pretty well because they're like the biggest brewery, or they were like the biggest brewery in the world for like 100 years or something like that. But anyways, so kind of a cool story. But the moral of the story though is that we still use it the same way. And so what we were thinking originally, we said, you know, this works really great. So instead what we do is we're going to substitute the population standard deviation with the sample. But then we're going to have to get this multiplier off the t-table. And we don't have time right now, but tomorrow that's what we're going to learn how to do. Okay? We're going to learn how to get these multipliers off the t-table so that we can make t intervals rather than z intervals and still keep our confidence. So, all right? That's where we'll pick up tomorrow.